This is a follow-up to the last screencast on relative velocity. I want to do a little two-dimensional work because that's what the chapter is about here, but I wanted to show you a little more 1D to get your notation up to speed and get you to feel comfortable with it. So here I have an example where there's runners. I have Alice, Bob, and Charlie, and Alice is running at 8 miles per hour. The way we've defined the coordinate system to the right is positive. She's going at 8 miles per hour. Bob is going at 10 miles per hour. And Charlie is going the other direction towards them, so it's a minus 8 miles per hour. And this is all relative to the road. So the yellow here is the road, and if we're sitting at spectator and we're still, we're fixed at respect to the road, we could say this is how we would see them if we're standing on the sidelines here. And then we might ask ourselves, well, what does it look like to Alice how Charlie or Bob are moving towards her? What does it look like to Bob? What does it look like to Charlie? So let's start with Alice. If we're in Alice's universe here and things are relative to her, we're going to want to have the A on the subscript come next. So let's see, what does it look like to her, what Bob is doing? So V, B, A, we put the A second, and in words we say this is the motion of Bob relative to Alice. Now, what I need to do is I know these things relative to the road, so this would be great if I had this. If I had Bob relative to the road, and then I could add it, like vector addition, to the road relative to Alice, that would do it. Now again, when I have the inside, when the inside subscripts of two vector addition, when they're the same, it's as if those cancel out. So VBR, RA, they leave me with just the outside here, BA. And remember, we know that the road relative to Alice will be just the flip of this. If I flip these subscripts, I flip the sign. So this is not so hard to do. And again, maybe this is intuitive, but so this would just be 10 miles per hour, because that's Bob relative to the road. And now we do minus, we're adding the minus 8 miles per hour, which is, we know that Alice to the road is 8, so road to Alice must be minus 8. And that's going to equal minus 2. Sorry, not minus 2, it's going to equal positive 2. It's going to be a plus 2 miles per hour. And this actually makes a lot of sense. If we're in a coordinate system on Alice, and Alice doesn't think she's moving, and she's moving almost as fast as Bob, Bob is still getting ahead of her, but at a rate of 2 miles rather than at a rate of 10. So from someone watching, Bob is getting ahead at a rate of 10 miles per hour, but to Alice, who's moving not as fast as Bob, but she's still moving, he's not as gaining as much as someone who's looking from the road. We can think about it another way. If they're moving at the same speed, it doesn't look like they're moving at all, right? If Alice and Bob are moving at the same speed, they maintain the same distance. It looks like there's no motion at all because relative to each other, the distance isn't changing between them. Let's do another one here, and then we can move on. So maybe we'll put that up there. And then we could pick whatever we want. Let's do something with Charlie. How about we do Bob relative to Charlie? So that question then would be, what is the velocity of Bob relative to Charlie? So then we're in Charlie's world. And just for my little algebra here, wouldn't it be great then if I could do Bob relative to the road plus the road relative to Charlie? That's great because these inner subscripts cancel, and they leave me just with what's on the outside. So this would be Charlie's point of view. And so Bob relative to the road, we know that's just the 10 miles per hour. And now road to Charlie is going to be Charlie flipped here. We have Charlie to the road, so it's going to be a plus 8 miles per hour, which is going to appear to Charlie plus 18 miles per hour. Now, I didn't talk about the sign on the last one. In these cases, these were both positive because from the viewpoint of that person, it's as if the other person is coming towards or away from them at the right. So let's go back to, in the case of Alice. Alice, Bob is actually moving away from her, but moving away from her to the right, so it's positive. Bob, it looks like that, to Charlie, it looks like that Bob is coming towards him. But again, because Bob is coming towards him to the right, it's positive. And these velocities add because they're coming towards each other. It's at a rate of the sum of these two. Here I have a problem set up in 2 dimensions now. So these are runners Alice, Bob, and Charlie again, but now we're looking at them on an overhead view. You could think of maybe tracking someone on Google Maps or Map My Run. And here they're running in these different directions, and X is defined, positive to the right. That's what this axis is showing. And Y pointing up here is up is positive and to the right is positive. Okay, and so we're going to say that Alice is running straight in the y direction, or north it could be, at 3 meters per second. And this is relative, this is a road. We'll say these are all roads. So relative to the road on this overhead view, she's running 3 meters per second. I like this notation. If you don't, that's okay. But this says, I can just leave it here, that says positive 3 in the y direction. Y hat means y direction. Just a shorthand notation. But the way the book says is we would say V Alice relative to the row of her y component is 3 and her x component is 0. That's the same thing here. There's no x, so that's 0. Likewise, Bob here is running at an angle of 45 degrees to the y-axis there, so northeast. And so he has a speed of 2.8 meters per second. His x component is, and his y is 2.8. The magnitude of this, if we actually solved it, we'd find out he's running 4 meters per second northeast. But if I split into the x, y components, this is what it is. I've already done it for you. But if you wanted to take the sine and cosine of 4, you'd get 2.8 and 2.8 roughly. So his x component, I like this notation. It says he's running, his x component is 2.8 meters and his y direction component is 2.8, but your book writes it like this. So 2.8 meters per second in the x direction and 2.8 in the y. This is Bob relative to the road, his x component, Bob relative to the road, his y. And then we have Charlie relative to the road is in the minus x direction. So that's, this x hat means x direction. But here's the way your book writes it. His Charlie relative to the road in the x direction is minus 3, and there's no y component. Oof. Okay, so now let's make a problem out of this. Let's see what it looks like in Bob's view. So Bob's the center of the universe. Now, what Alice looks like. So how would we find VBA for this problem? It's the exact same. It's just now we have to worry about the x and y components. We can't just before, because we had everything was in x, we just could add and subtract. Here now, if we're adding vectors, and you've done this before, we have to be careful to find their x components and only add their x's together, and then we keep that separate. And then we add their y components and only add those together and keep them separate. So if we want to find Bob relative to Alice, so this is what Bob looks like from Alice's point of view, just like before, we'd go, well, do we know V be to the road? And then do we know V road to Alice? Because that would do it in our notation system, where the the roads cancel out because of the inner, and it leaves us the outer subscript here. Okay, so let's do that. Let's shrink this first. And we can put it here. And let's see if we have everything we need. Okay, so Bob to road, that's right here. It's this, again, if you don't like this notation, it's okay. Look, he's going north 2.8 meters per second. Sorry, north 2.8 meters per second and east 2.8 meters per second. That's good. So we have that vector here. But do we have road to Alice? Well, we have Alice to road. Remember, the rule of thumb is if we flip these, we just flip the sign. So road to Alice is just going to be, if we do the notation like the book does, it's going to be, we're going to flip both components. It's going to be the minus of both those in order to get, so let's write those down. So V road to Alice y is going to equal minus 3 meters per second, and V road to Alice x, it's a little silly to write this again, but that's okay, is 0 flipped. It doesn't have a sign. It's still 0, so that remains the same. So let's box these because we need these. And then let's see if we have what we need for our result down here. All right, and now remember, when we're doing vector addition, we have to add the x components of what we're adding and the y components. So let's look at our whole new vector here. VBA is going to be equal to, let's just write down the components now. VBA, the whole thing, the x components are going to be, so the x component of BR is 2.8. okay? And the x component of RA is 0. So that one's going to be 2.8 plus 0. We can write that whole thing down. So it's going to be 2.8 meters per second plus 0 meters per second. Okay? And the VBAY component is going to be the two y components added together. And so this is going to be minus, we'll start with the BR. The BR is going to be the y component here is 2.8 again. So that's 2.8 meters per second. Ooh, minus 3 meters per second. Okay, let's see if we can make that smaller. Move those a little bit. All right, and then we'll find out, so the entire sum there of each of those components, this one's just going to be equal to, it's going to have 2.8 meters per second, but this one is going to be equal to a minus 0.2 meters per second. Let's box that. So what does this mean? Let's take a step and look back at it, because this is a little tricky now. So again, our question was, we're in Alice's universe here, and what does it look like? What does Bob's motion look like if we put the origin here? Here is 0, and what does the velocity look like? So Alice is going at a pretty good clip here of 3 meters per second. Bob is going northeast at 4, but his y component, his y component is 2.8. Alice's is faster, okay? And his x component is 2.8. So to Alice, it looks like, because she's gaining on Bob, it looks like Bob is going this way. To her, it looks like Bob is coming towards her, and because he's going down, she's eventually going to, because she's going faster, she's eventually going to catch him, and he's going to end up being also behind her in position. But again, this is velocity, this isn't position. So in velocity, to her, it looks like he's, she's slowly reeling him in the y direction. So it looks like he's coming down. But he's also going away because she doesn't have any x component here. He's still moving away to the right at a rate of 2.8 meters per second as well. Okay, so try to imagine that. We know the motion is going like this. They're both moving at the same time. And so they're getting farther and farther apart in x, but at some point in y, Alice is going to catch up with him and then move beyond him as well. Now we can put that to the kinematic equations, and we could find out like how long does it take them to meet up. So let's do that on the next slide. So let's turn this into a kinematics problem, and this is very similar to the car one. I could ask you a number of things. In this case, let's just recap real quick. Bob is moving northeast, so we split his components up on the other slide to find out his x and y components, and we know that Alice is just going due north. However, from Alice's point of view, we have VBA from her point of view. To her, it looks like in the x direction, Bob's just moving away at a rate of 2.8 meters per second. In the y direction, she is slowly catching him. So to her point of view, it looks like he's coming backwards towards her in the negative y direction. And so the question, how long before she reels him in the y coordinate, so the same latitude. So we're really only interested in this part of the problem here. That's the beauty of kinematics. Even in 2D, we have an independence between the x and the y coordinate. I could also ask, like, how far away in x does he get at that time? That could be a follow-up to the problem, but let's find out how long before they get to the same latitude. So let's use y, because we're interested in the y coordinate, and we're going to say y, b, a. So again, this is Alice's point of view. So this is the final position to Alice's point of view of Bob. And this is the same as the kinematic equation we've used before, but you just have to be really careful with the subscript here, is going to be where Alice thinks that Bob started, plus the velocity that she thinks Bob is going. I should put in the y direction here, times t. Okay, and then let's write in what we know. So where Alice wants Bob to end up, or wants to know, that's this one down here, is 0. This is that meeting point, so that's going to be 0. Now again, she thinks she's the center of the universe. So where does Bob start at when we start our stopwatch in this problem here? That would be the scenario right here, and that would be 10, a plus 10. So she thinks he's a 10 kilometer away, and we know that she thinks that he's coming to her at a rate of minus 0.2 meters per second. Okay, if we, let me shrink that down. This is a pretty easy equation to solve. My variables are all not grouping together well, but that's okay, we can still do it. So if I go up here, I'm going to have to, what I want to do is I want to get the 10K out of here. Hope I lost the T somewhere. Times T. So I'm going to get rid of the 10K by subtracting from both sides, so there'll be minus 10 kilometers. It is going to be equal to minus 0.2 meters per second T. Okay, and then to solve for T, I'm going to divide by minus 0.2. So T is going to be equal to minus 10 kilometers divided by minus 0.2 meters per second. Okay, and we're going to have to do a little bit of unit conversion on this one. Let's actually just move to a clean slide. Okay, so that will be T equals 10 kilometers. So the K is 1,000. It's actually right there. That's going to be 10,000 meters. The minus signs cancel, so I'm just going to write this down on top. We'll write 10,000 meters divided by 0.2 meters per second. Let's do the numbers first. So that's going to be 10,000 divided by 0.2. And then we're going to have meters divided by meters per second. So that's going to be equal to 10,000. And that's going to be meters times the reciprocal of the bottom. It's going to be second per meter. Oh, and I forgot my 0.2. So that's going to be 50,000 seconds. Let's move that over and let's do a conversion. Okay, so that 50,000 seconds, if I want to get to minutes, let me make an empty fraction. I'm going to put seconds on the bottom so they cancel. Minute on top, and I know that there's 60 seconds in 1 minute. And I can already tell that that's going to be still a big number. So let's go further. Let's make another fraction. Let's put minute on the bottom to cancel minutes. So that goes and then there's going to be 60 minutes in 1 hour. And then minutes cancel. And then it turns out that if I do the math on this, this is going to be 13.9 hours, which is a long time, but they're going nearly the same rate in the y direction, and so Alice is slowly, but she is catching up to Bob, and it's going to take her 13.9 hours to get there. Now what we could do, I won't do it in this video, but we could say, okay, that's 13.9 hours or 50,000 seconds for them to reach the same latitude. I could take the x components and do the same thing and find out how far away that Bob got east in that time. So then I can know exactly from Alice's point of view at 13.9 hours where Bob is at that moment. That's all for this screencast. There are some nice problems in your book with boats relative to the water in a stream, or a plane relative to the wind, and it's the same notation. The part that is really challenging is just setting up the vectors, and as long as you remember to cancel out that inner subscript, you'll get everything right, and the rest is just the regular kinematic equations.